Latitude Media, podcast at the frontier of climate technology.
I'm Shail Khan, and this is Catalyst.
If you were to fully electrify this process, that might be something like 4 gigawatts of electricity, average load. Not peak load, average load. So we're talking about like 4 nuclear power stations to run 1 normie steel mill.
All right, steel yourself for a conversation about decarbonizing the world's most extracted mineral.
Catalyst is supported by Kraken, helping utilities support customers in the transition to a greener world. Already licensed by major players across the globe, including Origin Energy, E.ON, and EDF, Kraken is helping utilities offer excellent customer service and develop innovative products and tariffs through the connection and optimization of smart home energy assets. Click the link in the show notes to learn more, or go to kraken.tech. That's Kraken, kraken.tech. Kraken, energy technology upgraded.
Would you be interested in seeing solar module price trends based on real quotes? Now you can with ANZA's free quarterly Module Pricing Insights report. ANZA is a data analytics and service platform that helps solar module and energy storage buyers make optimal decisions. ANZA has compiled pricing data for more than 95% of the U.S. supply to show you insights over the last 3 months. To learn more, click the link in the show notes.
Catalyst is brought to you by Antenna Group, the global leader in integrated marketing, public relations, creative, and public affairs for energy and climate brands. If you're a startup, investor, or enterprise that's trying to make a name for yourself in climate's age of adoption, Antenna Group's team of industry insiders are ready to help tell your story and accelerate your growth engine. Learn more at antennagroup.com.
I'm Shail Khan. I invest in revolutionary climate technologies with Energy Impact Partners. Welcome. All right, so go to your computer or your phone or whatever and Google all the metals we mined. If you look that up, you're going to find a graphic that I really love that shows how much we globally extract various ores and metals on an annual basis. And I'll give you the top 5 so you could skip the graphic if you want. It's starting from the bottom. Number 5, manganese, 20 million tons a year. 20 million tons. Just think about how much that is. It's a lot. That's manganese. Copper, 22 million tons. Chromium, 41 million tons. Aluminum, 69 million tons. So that's number 2. 69 million tons of aluminum per year. And then there's iron ore, which is number 1, and which is what we use to make steel. That's 2.6 billion tons. 2.6 billion tons per year. That, my friend, is why decarbonizing steelmaking is a really big deal, because we produce so much steel. And of course, it's one of the quote unquote hard to abate sectors, along with stuff like cement. But it's also one where an interesting set of pathways has emerged, ranging from using hydrogen to directly electrifying to maybe a little bit of better recycling. Anyway, Rebecca Dell, our guest this week, is the industry program director at ClimateWorks and is one of my favorite people to talk to about all industrial decarbonization stuff. This time we talk steel. Here's Rebecca. Rebecca, welcome.
Thanks so much for having me, Shail.
Great to have you back. Let's talk about steel, starting with why steel is a problem. How big a problem steel is from an emissions standpoint. We know it's big, largest source of industrial emissions, but just like contextualize for me how much steel we produce and how much greenhouse gas emissions that produces today.
Sure. So making steel emits more greenhouse gases than anything else except making electricity. So it's a big number. The total emissions of the global steel industry from all sources is a bit more than 4 billion tons of CO2 equivalent every year, which means that it's, maybe like 8-ish% of greenhouse gas emissions, depending on exactly how you count it. So that's the short answer for why steel is a problem that's worth thinking about from a climate perspective. When we break down where those emissions come from, first, we make something like 2 billion tons a year of steel globally, which is just a crazy amount, right? Like, that means that we're making more than 500 pounds of steel per person per year for every single human being on the planet. So depending on how large a person you are, that's like between 3 and 4 times your mass as a human worth of steel every year, year after year. Within that, steel is actually a really highly recycled material. So like 1/3 of that 2 billion tons is recycled steel, which has relatively low emissions. 2/3 of that is steel that we make from iron ore, new steel made from rocks, and more than 85%, between 85 and 90% of the emissions come from that new steel made from rocks. You might imagine that's a more energy-intensive process than recycling.
Right. And we're going to talk about where those emissions come from and how to mitigate them. But on recycling, before we move on from that, what percentage of steel is recycled? Like, I know the percentage of new steel that has been recycled, but how heavily recycled is end-of-life steel, I guess is the question.
Steel is actually the most recycled material of all, full stop. It's really, really easy to recycle. It recycles beautifully. And it's also, in addition to being, you can melt it down and you can make new steel products out of it very easily. It's very easy to separate from other materials because it's magnetic. So if you have like a bunch of mixed metals, you can just put a big magnet next to them and pull the steel out. In places where we have good statistics, which tend to be higher income countries, we usually find something like 85% of end-of-life steel is collected and recycled. That's probably pretty close to a practical limit. We might be able to push that up to 90%, but you're never going to get all of the steel. Some of it is ruined. Some of it is like embedded in concrete that's at the bottom of the ocean. Like there's always going to be some that you don't get. And so we do a pretty good job.
So the implication then is if we're recycling 85, 90% of end-of-life steel, but that recycled steel represents only 1/3 of new steel production, it's because of economic growth predominantly. Like if economic growth globally stopped tomorrow, then our demand for greenfield steel production would drop to not zero, but fairly near zero. Is that the right way to think about it? That like that excess steel production is largely a function of a growing global economy?
So there's a big lag in that process because we mostly use steel to make durable goods. And so if you put steel into a vehicle or a piece of industrial equipment or a building or a piece of infrastructure, it might be there for 10, 20, 50, 100 years. And so you can imagine a situation where the economy stops growing, and eventually you get to that steady state, but it would take decades to get there because of those lags. Though it's also the case that demand for steel tends to saturate. So, of all the things that I listed, like, buildings, infrastructure, vehicles, equipment, those are things that, like, when a country moves from being low income to being middle income, they're buying all of those things and building all of those things for the very first time, and that requires a ton of steel. Once you've sort of been sort of upper middle income or higher income as a society for a while, you already have those things. And so you only need to replace things as they wear out, and maybe you have a little bit of population growth or a little bit of economic growth. And so demand for steel really tails off once a country has been rich for a while.
So independent of recycling, there's, as you're saying, we could maybe get a little better, but we're pretty good on recycling. So that's probably not our solution, nor is quitting economic growth, presumably. So we're going to produce a lot of new steel in any given year. So we need to decarbonize it. Let's talk about how we produce new steel today, and where those emissions come from. So you just walk through I know there are multiple pathways to produce steel today. So break down how we do it.
Absolutely. And to be fair, I love recycling. Recycling is wonderful, and we should keep doing it. The point is just that, like, we're already doing a pretty good job at it, so it's very hard to get any additional benefit from recycling in our current situation. So, as you say, we expect, like, because of we've had growing demand for steel, we have things are being used, they're making it to end of life. So the total supply of scrap is going up over time, but it's going to be a very long time before the demand for new steel goes away, and it's actually probably going to be a long time before it even goes down. So how do we make steel? Or how do we? The first thing we have to do is make iron. We usually split the process into 2 steps. So step number 1 is the iron making process. That's when you take a rock and you turn it into a metal. And then step number 2 is the steel making process, where you take the metal you have and turn it into the metal you want. As you might imagine, turning a rock into a metal is like a much more energy intense and greenhouse gas intense process than turning the metal you have into the metal you want. So the iron making process, that's really where the major driver of all the greenhouse gas emissions from the steel industry come from. And more than 90% of iron made today is made with the single piece of equipment, which is called the blast furnace. So the blast furnace is actually kind of amazing. If you talk to chemical engineers, they're like, oh, it's the world's most perfect reactor. So it's this giant thing. It's like usually at least 150 feet tall. And what you do is you put coal and iron ore and a few other small amounts of a few other things in the top. As that material settles down through this very, very tall column, part of the iron is burned, or part of the, rather, coal is burned to provide heat to drive the chemical reaction. And then the chemical reaction that you want is that the other part of the coal is actually reacting with the iron ore to purify it and change it from iron oxide, so iron atoms chemically bonded to oxygen atoms, into just pure metallic iron. And the metallic iron comes out the bottom.
And to be clear about what that part is, right, you're trying to remove the oxygen from the iron oxide. And the way that you do that is you bind it with the carbon in the coal. Of course, carbon and oxygen combine becomes CO2, right? So you've got your dual problems, not dissimilar from cement in this context, which is you're both burning coal, hence emissions, and you have a process that inherently produces CO2. That's sort of the point.
Yeah, there's 2 different sets of chemical reactions that are happening inside the blast furnace, and they're both making CO2.
Right. And that's why coal is such a perfect fit for the blast furnace too, right? Like it is doing both of those things, and it does them very well, and that's why coal is the perfect feedstock for a blast furnace iron-making process.
Yeah, and it also is actually doing mechanical work inside the blast furnace too, because unlike other forms of fossil fuels, coal is solid. And so you can use the actual like solid strength of the coal to control the rate at which the iron ore is traveling through the reactor. And so you can't easily swap out a solid fuel for a liquid or gaseous fuel.
Is that why it doesn't make sense to put natural gas in a blast furnace, for example, and try to replace coal with natural gas?
So people do sometimes put natural gas into the blast furnace, but basically what you're doing in that case is you're just trying to substitute for that portion of the coal that gets burned for heat energy. So you can inject some natural gas to get you some more if that's economical. People also will just pulverize coal and inject that into the blast furnace to provide that extra heat energy because metallurgical coal is very expensive compared to normal coal, and it's even sometimes expensive compared to natural gas. But like that's never going to be more than a partial substitute.
Okay, so you mentioned that this process, the blast furnace process, is something like 90% of new steel production. The rest mostly is the DRI process, right? And people talk about that a lot in the context of decarbonization, which we'll get to a bit later because hydrogen in a DRI process is one of the pathways. But I think it's worth starting by appreciating that DRI represents a pretty small portion today of new steel production. But what is DRI?
Yeah, so DRI stands for direct reduced iron. And so, as I said, more than 90% of the iron making that happens today happens with the blast furnace in that coal-based process. So, but DRI, it's less than 10% of current iron making, but we started this conversation by saying we're making 2 billion tons a year of this stuff. So even a small portion of the global steel and iron industry is like a big industry and a fully commercial technology that's used at dozens of sites around the world. And so the way the DRI works is that instead of using a blast furnace, there's a different kind of furnace that's usually called a shaft furnace. And similarly, what you're doing is that you are putting your iron ore in the top and then putting fuel that can do that chemical reaction that strips off the oxygen atoms from the iron ore in the bottom and having the two kind of move past each other and react with one another. But the DRI process is designed to use a gaseous fuel instead of a solid fuel. So almost all of the DRI that's done in the world today is done with methane, but sometimes it's done with hydrogen that is made from coal or other dirty sources. And in theory, you could do it with hydrogen from clean sources, which, as you say, is one of the kind of fastest moving decarbonization pathways that we have in the steel industry.
Right. So I want to get back to the hydrogen DRI thing, but as you said, most of the DRI today is using methane, it's using natural gas. Just from an emission standpoint, per ton of iron produced, how big of an emissions savings do you get if you do DRI with natural gas versus a blast furnace with coal?
It can be really large. So if you look at like the total process of the iron making and the steel making together, for just like a very typical conventional blast furnace facility, you're usually going to end up with more than 2 tons of CO2 per ton of steel, which is kind of like, it's worth pausing on that basically almost every steel mill in the world is making more CO2 than steel. Its primary product is CO2. But if you use today's technology and fossil fuels, and you kind of max out everything that you can. So you electrify everything in that process that we know how to electrify, that we have mature electrical technologies for today, and you use clean electricity, and you use methane DRI, and you use low leakage methane for low upstream leakage methane techniques. You turn all of the dials up to 10, but no new technologies, just stuff that's fully commercial today. You can squeeze that down to under 1 ton of CO2 per ton of steel. And that is, to my knowledge, there's basically one facility on Earth that is an example of that. Which is not a particularly virtuous facility. It was not built this way for climate reasons. It just happens to be a methane DRI plant that's in Quebec. And Quebec's grid is almost all hydro, and the electricity is very, very cheap. And so they just for purely economic reasons, they built it as a highly electrified plant. And then they have perfectly clean electricity, and you put it all together, and you can squeeze it down to less than 1 ton of CO2 per ton of steel. But if you're making 2 billion tons of steel per year, or rather if you're making like 1.3 billion tons a year of steel from iron ore, that's still too much.
And is that the reason why we don't do more DRI today? Like, why is it only 10%? It's just an economic thing. Coal is cheap.
It's purely economic. There's a few places in the world where you can get energy from methane, from gas, that is economical for the steel industry. And so in the places where the gas is cheap, people do some DRI, but in most of the world, coal is much cheaper.
Okay, so obviously we got to figure out how to do better even than 1 ton per ton. So let's talk about the decarbonized pathways to produce iron that are emerging. We've already alluded to one, so let's start there, which is hydrogen DRI. Just talk a little bit through. I mean, it's not quite as simple as just like swap in the hydrogen, swap out the methane in those reactors. So, what is the technical challenge to doing hydrogen DRI, and then how much promise is there versus like where are the limitations?
Yeah. So hydrogen DRI is like the most advanced option for fully decarbonized steelmaking. I think about it as like that is the smallest increment of new technology that we need to get to like fully or like near zero greenhouse gas emissions steelmaking. And the reason why it's a relatively small increment of technology is that, we have this DRI process that's already a commercial process, and you don't actually put the methane directly into the furnace. You make syngas, so a combination of carbon monoxide and hydrogen gas, and that's the gas that's currently used in the in shaft furnaces around the world. And so we're already doing a bunch of steelmaking with hydrogen. It's just mixed in this syngas. And so the companies that make these furnaces, they all say that basically you can get up to 70% hydrogen with no changes. You can just keep operating your furnace as normal with up to 70% hydrogen. And so the first and easiest thing to do is you can just start enriching the amount of hydrogen that you put into existing furnaces. There are some technical challenges if you want to go from 70% to 100%. And those have to do with things like how much heat is generated in the reaction, and so keeping your furnace at the correct temperature, making sure that you get what's called full metallization, so that as close as possible to all of the iron atoms are converted into metallic iron. You don't have any leftover iron oxide at the end. So these are real technical challenges, but they're very much in the domain of engineering challenges for a functional technology. We're talking about re-engineering a technology that we know works. There's no new science that has to be discovered here or anything. So I have talked to at least dozens of people in the steel industry over the years, and I've literally never heard anybody be like, I don't think hydrogen DRI is going to work. Everybody believes it will work. The only hesitations about it there's two of them. One, there's a lot of hesitation about where's the hydrogen going to come from and how much is it going to cost? So is this thing going to be economical? And two, the current DRI technology requires a higher quality iron ore than a blast furnace does. And so we could not take... If we were just going to use the iron ore that we are currently mining, we can't straightforwardly just put all of that in a shaft furnace, even if we built enough shaft furnaces. And so there's a wide range of opinions in the steel industry about how much of a problem this ore quality issue is going to be. But at a minimum, we're going to have to develop some new engineering processes to upgrade the quality of iron ores to make more of them viable for DRI.
Which comes at a cost. We don't know exactly how high the cost is yet, but comes at some cost.
Everything comes at a cost. And, steel is wonderful. There are reasons that there's so many reasons why we use so much of it. That 2 billion tons a year, that's because we use it for everything. And we use it for everything because it's strong, it's stiff, it's durable, it's formable. It has a variety of valuable both thermal and electrical properties. It's great. But maybe the most valuable thing about it, or the most attractive thing about it, is that it's cheap. And so that is a characteristic that we very much would like to retain in a decarbonized future.
Catalyst is supported by Kraken, the advanced operating system for energy. Kraken's technology helps manage and optimize renewable generation, supports the upgrade and maintenance of the network, and helps utilities deliver excellent customer experiences. Currently managing 42 gigawatts of power, optimizing 160,000 distributed energy assets, and supporting 54 million customer accounts worldwide, Kraken is revolutionizing the industry from generation to supply. Learn more about how Kraken can help you create a smarter, greener grid at kraken.tech. That's Kraken, kraken.tech. Or just go to the link in the show notes.
Have we hit a solar module price floor? What are the impacts of the anti-dumping petition submitted in April? Answers to these questions and more are now available in ANSA's Q2 Module Pricing Insights Report. In case you haven't heard of them, ANSA is a data analytics and service platform that helps solar module and energy storage buyers make optimal decisions. ANSA's clients save time and money while also reducing risks during due diligence and procurement. ANSYS free Pricing Insights report compiles data from its platform, which covers 95% of the U.S. module supply. Learn about the latest trends by clicking the link in the show notes.
Catalyst is brought to you by the Antenna Group. Antenna, they are the OGs of PR and marketing for climate tech. Is your brand a leader or challenger? Are you looking to win the hearts and minds of customers, partners, or investors, ramp up your new business pipeline, influence policy conversations? Antenna works with leading brands across the energy and climate ecosystems to do all of this and more. If you're a startup, investor, enterprise, or innovation ecosystem that's helping drive climate's age of adoption, Antenna Group is ready to power your impact. You can visit antennagroup.com to learn more.
Okay, so that's hydrogen DRI. So as you said, the two big questions are how cheap and clean can the hydrogen be, and how do you deal with the non-high-grade ores? Let's talk about at least two other decarbonized pathways, one which is direct electrification and the other which is carbon capture. Maybe starting with direct electrification. So as you said, hydrogen DRI is the smallest increment of technological advancement required. The higher amount of technological advancement required is to just directly electrify the process. So there are multiple different potential ways to do this and companies working on it. So can you just explain at the high level what that would have to look like?
Sure. And much like with the DRI, there is an existing analog in our current economy, which is aluminum. We already use a directly electrified process to make aluminum. And so the idea that you can do metallurgy at scale and you're basically doing a similar type of reaction. You have aluminum oxides and you want to convert them into metallic aluminum. And we do that with electricity today. So conceptually, you think, okay, this is a thing that should work. Again, it's a question of exactly how is it going to work and how much is it going to cost? And just generally, if we think about the hydrogen DRI process, you need a bunch of hydrogen. Where's that hydrogen going to come from? Well, most people who care about climate, their preferred place that hydrogen would come from is that you start with water and you use electricity to split the hydrogens from the oxygens in your water, and that's where you get the hydrogen. So that's an electrified process too. It's just an indirectly electrified process. And every time you do one of those conversions that, you go from electricity to hydrogen and then hydrogen to another thing, every time you go from one thing to another thing, you lose a lot of energy. So if we can just go direct consumption of electricity in our iron making, that is going to significantly reduce the total amount of electricity that would be required, which, is good. That both makes it cheaper, but also it's a serious question. Where is all the electricity for this industry going to come from? Because just to kind of give people a sense of scale, for a typical, what we call integrated mill, so that's an iron-making facility or a steel-making facility that uses a blast furnace, not a big one, just like a dead normal-sized integrated steel mill. If you were to fully electrify this process, that might be something like 4 gigawatts of electricity. Average load, not peak load, average load. So we're talking about 4 nuclear power stations to run one normie steel mill. We're talking about a lot of electricity here. And so if we can save the 25 or 30% of the electricity that we would lose converting to hydrogen in the middle, that would be very valuable. But these technologies are not as mature as DRI. These are larger steps forward in the world of technological innovation. There's a few different pathways that people are interested in. There's one that's called molten oxide electrolysis, which sounds pretty much what it sounds like. You start with your iron oxide, you heat it up until it's molten, it melts, and then you do electrolysis on that. There's also aqueous electrolysis, and there are kind of up-and-coming companies that are working on a few different pathways here. And some of them are getting close to their first commercial deployment, but none of them are there yet.
And is there a fundamental, first of all, we should reference the benefit that they have relative to today's hydrogen DRI, which is that those processes do not generally require the high-grade ores.
No. In principle, many of these processes, you can use totally trash ores.
So is the right way to think about it that all things equal from a first principle standpoint, if you can get one of these pathways to work, it should be lower embodied energy than hydrogen DRI. It should use a wider variety of ores more easily. So all things equal, direct electrification is the way to go. It's a question of, can we make it work and at what cost?
100%. It's like the kind of like engineering fundamentals of it are very attractive. It's just like, we have, with hydrogen DRI, we have a process where we're like, everybody believes it will work. Nobody's sure if it will scale. With these direct electrification approaches, people are much more toward the like, yes, we believe it could scale, but we're not sure whether or not it will work.
And where are we in, like, what's the furthest along any one of these pathways is?
So the most mature of these efforts is a company called Boston Metal,
which I should note we are investors in at EIP for full disclosure.
Yes. I am not an investor in it, so I'm not talking my book, but, everyone should be careful what Shale says.
That's right. I'll stay very silent for the next couple sentences. Go ahead.
Yeah, but no, so Boston Metal is doing molten oxide electrolysis. They're also trying to solve that anode problem that you mentioned, they're developing what are called inert anodes. They are very, very close to their first kind of commercial deployment of a cell, and they're planning for their technology to be a modular one. So like once one or two cells is deployed, a bigger facility would just be more cells. So they're hoping that will make scaling quick. But what they have deployed they've used their technology on other metals, what are called ferroalloys, and they've used their technology with carbon anodes, not the fancy inert anodes they're inventing. And those things seem to work, but we're still waiting for the commercial deployment of the actual iron-making cell, which should come in the next, I think, year or two, but honestly, you would know better than me.
Like I said, I will stay silent on this part, but yes, that's an accurate depiction, I think, of where they are. Okay, so hydrogen DRI, pluses and minuses, direct electrification, pluses and minuses, lots of pluses if you can get it to work, but that's the question
mark. That's a big minus.
Yeah, that's a big minus. That's more of a question mark.
It would be a big plus to not have that question mark.
Sure would. Well, let's talk about the third thing people talk about to decarbonize steel production, which is CCS. We've talked about CCS before on the show in the context of lots of other industrial processes or power plants or whatever. Where are we with carbon capture as it pertains to steel?
Yeah, so I'm not opposed to carbon capture in principle. Like, I'm open to considering it. But honestly, there's very little going on in the world of carbon capture in the steel industry right now. There are no large-scale efforts to commercialize this technology. Like there isn't a single steel company anywhere in the world that's like, we're going to do this at scale on an entire blast furnace, and we have a plan for doing that in the near future. When people talk about it, it's in very, very vague terms. And there are some CCS initiatives that are out there, but they're all like weird little ones that won't scale. Like they're very clearly not designed to get to high capture rates on a facility level. And so, like, as I said, I'm not opposed to it in principle, but when I survey the landscape, I don't see anyone who's pushing it forward in a serious way. And in the absence of that, I'm sort of like, clock's running out, guys.
So why not? Like, why is no real action happening on CCS and steel?
So I think that my read on the situation is that the thing that people like about CCS is that it, in theory, allows you to keep doing fundamentally the thing that you're doing right now, but with lower environmental consequences. You get to kind of keep using the same process and ideally the same equipment, but instead of putting your trash in the atmosphere, you capture it all and you stick it underground. That's the conceptual appeal. The problem is that when you start looking at the details, it's actually really, really hard to do that at a steel mill. Because if you look at a steel mill, typically what you find is that there are a few things that have really, really large amounts of CO2 kind of coming out of one pipe. Your blast furnace, your basic oxygen furnace, things like that. But those big CO2 sources, those only add up to typically 60% of the CO2 on site. And all of the rest of the CO2 is coming out of dozens of little reheat burners and things in random places all over the site. And so you could imagine doing a retrofit on a blast furnace and figuring out a way to do CCS on that, and these other large sources, and having that pencil out at a reasonable cost. But if you wanted to get big reductions site-wide, then you have to start going after all of those dozens and dozens of little sources, and it's never going to be cost-effective to do that. And so I think basically what has happened is that people have realized that if you want to get really high capture rate CCS in a steel facility, you actually are going to have to pretty fundamentally redesign the processes. And so you're not actually going to be able to keep all of the equipment in the way that you had hoped to. And so in the absence of and that really undermines any economic case you might be trying to make for it. And I think that's a big part of why people, honestly, 10 years ago, before steel decarbonization was cool, a bunch of steel companies were investing in CCS pilot projects, particularly European steel companies, and they did a bunch of these little pilot projects, and then just none of them went anywhere. And I think this is my understanding of why that's the case.
Okay, so moving on from the technology pathways then, let's talk about the big players in this market. Who are the big steel producers? Where are they? Where are they producing? And do we have any indications at this point on which to the extent that they are serious about decarbonization, question mark, are they serious about decarbonization? Which direction does it appear that they are heading?
Yeah. So, okay. Geographically, half of all the steel in the world is made in China. So that's the biggest, that is as big as all the other producers put together. And so obviously that's the most important one. And China's interesting also because a lot of the major steel producers in China are actually state-owned enterprises. So those companies have a very different set of incentives than the steel company that your listeners might be more familiar with in the United States or another high-income country. And so these companies are interested in decarbonization. They're exploring it. And their primary motivation for that is that the Chinese government has stated and reiterated many times over many years now that China's emissions need to peak before 2030 and reach net zero by 2060. And so as state-owned enterprises, they perceive themselves to be bound by those requirements. But for them, it's a policy driver in most cases. It's not so much a market driver. Then we have big steel companies around the world. The largest private steel company is a company called ArcelorMittal, which is a European headquartered company and has steel facilities all over the world. The largest steel companies here in the U.S., there's two that do primarily recycling, Nucor and SDI, and then two that do primary steelmaking, which is U.S. Steel and Cleveland Cliffs. And then other kind of big steel producing geographies include Japan, South Korea, and the European Union, especially Germany.
And okay, so amongst the larger players, let's say, whether it's China or the ArcelorMittals of the world, I guess I think about this in comparison to maritime decarbonization, where you have we have Maersk clearly publicly making a bet, not entirely unhedged, but making a bet on methanol as the next fuel source for maritime. They're ordering a bunch of methanol-ready ships and investing in the methanol supply chain and so on. Is there an equivalent to that in the steel world yet, or is it still TBD?
So there are I would say, well, actually, until recently, I would have said there are 4. Now, maybe we can claim that there are 6 kind of serious, large-scale hydrogen DRI projects that are under development around the world. There's 2 in Sweden, 2 in Germany, and 2 in the U.S. The two in the U.S. are the new entrants on the list, who both of them made their debut a few months ago when the Department of Energy announced that each of them was going to be getting a grant from the taxpayer of $500 million. So the two in Sweden are often thought of as the most advanced. The Swedes have a very favorable situation here where they have a lot of undeveloped renewable electricity resources, cheap electricity. They also have the highest grade ore in the world. The Swedish government owns the LKAB, which is their iron ore mining company. And it's just like, it is the queen of the ores. And so they're very, very well set up for hydrogen DRI. Then the Germans, it's two companies, ThyssenKrupp and Salzgitter. And both of them, I think, from the German perspective, they see the writing on the wall. The European emissions trading system is not necessarily biting hard at their bottom line today, but it bites more every year. And the direction of travel is very clear. And the German government feels very strongly that they want to maintain their steel industry. And so they have pledged 3 billion euros of support to these two German companies, a combination of both capital support and hydrogen subsidies for them to do commercial scale hydrogen DRI projects. And then there's the two in the US. So those are the kind of that's what we're looking at as the race is on, who's going to get there first.
I guess final question for you. Is there any case for significant material substitution? Like the other possible way to decarbonize steel production is to produce less steel. Is there a world in which, in the absence of reducing economic growth, where something replaces steel for some applications? And as you pointed out, right, the benefit of steel, in addition to all of its properties, is its cheapness. But imagine that in the process of decarbonizing it, its cheapness is reduced somewhat. In other words, it becomes a little bit more expensive. Could you imagine material substitution here?
There are some places where we can have material substitution, or maybe more likely material efficiency, where we can provide the same economic service with less steel. That is actually, it's much easier to find opportunities for that than it is to find opportunities for material substitution. I would say the primary area of material substitution that people point to is mass timber, advanced timber, substituting steel as a structural element in buildings. I think that that's interesting, but it's got some really important limitations. One, really North America and maybe some small parts of Northern Europe are the only places in the world that have the trees. Everywhere else, if you did that, you would be driving deforestation that would make the whole thing counterproductive. And so and these are countries that are not, they're already developed, they're not building at a huge rate. And so it's interesting, it's real, I'm not against it, but it's not a huge bite. But there are tons of opportunities for using steel more efficiently. That includes really simple stuff like extending the lifetime of buildings and major capital goods. If you throw things out less frequently, then you need fewer new things. Also, we typically, when people do studies on these type of thing, they typically find that buildings use between 50 and 100% more structural material than is required to comply with building codes. And they do that because the structural material, mainly steel and cement, is very cheap. But if you made a concerted effort to not overbuild, there's more you could shave off there. So there's a lot of opportunities, but just swapping steel for something else is really hard. And I think that aluminum makes a great comparison. So the thing that the alternative that is sort of most proximate to steel is aluminum. And you do see some material substitution, steel to aluminum, particularly in light duty vehicles, in cars and trucks.
And planes and stuff.
Yeah, because it's lighter weight. And you're right, there's very little steel left in airplanes. It's all aluminum and carbon fiber at this point. But just like the basic manufacturing cost, typically for steel is, I don't know, maybe like $600 a ton. It's like $1,800 a ton for aluminum. So even if you don't need as much of it, the price difference is still very large. And basically almost every material except every metal besides steel requires more energy to make it than steel does. And so all of the other options, you're sort of like, oh yeah, that looks interesting. But then you start trying to think about, well, what would it mean for it actually to scale to the level of hundreds of millions or even 1 billion tons a year of steel equivalent? And then you end up seeing there's a small number of opportunities to make relatively small bites, but you always end up back in a place where you're just like, okay, steel's not going anywhere.
Yep. All right. Well, that's a good note to end on. Steel's not going anywhere, so let's figure out how to decarbonize it. Rebecca, this was fun as always. Thanks for coming back.
Thanks so much for having me, Shale. I had a great time.
Rebecca Dell directs the industry program at the ClimateWorks Foundation. This show is a production of Latitude Media. You can head over to latitudemedia.com for links to today's topics. Latitude is supported by Prelude Ventures. Prelude backs visionaries accelerating climate innovation that will reshape the global economy for the betterment of people and planet. Learn more at preludeventures.com. This episode was produced by Daniel Waldorf. Mixing by Roy Campanella and Sean Marquand. Theme song by Sean Marquand. Stephen Lacey is our executive editor. I'm Shale Khan, and this is Catalyst.